Hi everybody, Physics Ninja here, and welcome to my review on relative velocity problems. This is what we're going to do today. We've got 5 problems, 12 questions, dealing with all types of relative velocity problems. We have boats crossing a river, we've got planes flying in a crosswind. This is what you do. You go download the problem set and you try the problems out for yourself. After you're done, come watch the video solutions, see if you got the right answer. So, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. Alright, let's get started. Alright, here's problem number 1. It says the width of a river is 90 meters, and the water flows with a constant speed of the velocity of the water relative to the ground with respect to its banks. An athletic swimmer can swim at a speed Vs sub W of 6 meters per second in still water. Although she heads directly across the river, the opposite bank with her maximum effort, she ends up arriving at point C on the opposite bank, a distance L of 60 meters downstream. All right, let me first just enter some of these values here. So that's the width of the river is 90. And we also know that she ends up going like this, a distance L downstream. Okay, so the first question says, what is the speed of the water relative to the ground? All right, and we've got some numerical answers right here. All right, so what I would first suggest over here, let's just think about this a little bit. So the swimmer is swimming this direction over here, so that's the velocity of the swimmer with respect to the water. Okay, but now what we have is we have the water here is moving, all right, and the water is moving in this direction. So I write this as the velocity of the water here relative to the ground. So at the end, what it looks like is the swimmer is going to end up going along this green trajectory right here. So this is going to be the net velocity of the swimmer here, we would say, relative to the ground. The way you would write this now as an equation is I would say the velocity of the swimmer relative to the ground is equal to what? Well, it's the velocity of the swimmer with respect to the water relative to the water, plus the velocity of the water relative to the ground. Okay, so this is kind of our general idea. For this problem now, let's just think about this. If we're drifting 60 meters downstream, right, and it takes a certain amount of time to drift that distance right there. Okay, so let's go ahead and write down that equation. Right, we can see that the only thing that is making the swimmer drift is actually the speed of the water right here. So one thing I could right away I can write down is that the x displacement, in this case it's going to be L, which is 60 meters, is going to be the speed of this water relative to the ground, okay, multiplied by how much time it takes for her to get across. Okay. Now we don't know the time and we do know the length L, so in order for us to solve for V of the water with respect to the ground, we need to substitute time into here. All right, so let's think about time. So this is equation 1. For time, what we can do now is we can analyze what is going on here in this vertical direction. We know that my displacement is going to be y, and that is simply going to be d, the width of the river. And in that case, the only thing that has a component with a vertical direction, the only velocity here that has a component like that is the swimmer with respect to the water. So I'm just going to substitute that. So it's going to be the speed multiplied by the same amount of time it takes to drift downstream. So you can see from equation 2 right here, I could figure out what is the time because I know everything else. So the time in my expression is simply d divided by the swimmer relative to the water. All right, so right away you could solve for this. All right, so because the distance d is 90 meters and the speed of the swimmer relative to the water is given by 6. So that means we're left with a time of 15 seconds. So now we go back to our first equation and you can substitute into our first equation to solve for our unknown. Let me just write down the expression. So the speed of the water relative to the ground is then going to be L divided by that total time. This is 60 divided by 15 seconds is what we just solved for. So we get a speed of 4 meters per second. Okay, so 4 meters per second looks like choice D is the correct answer right here. So not a bad problem. All right, next question says, if instead she chose a heading that would get her directly across the river at point B, how long would it take for her to get to the other side? All right, we've got three choices. So let's go see. So really what she wants to do now is she wants to aim at some angle in order that her net direction ends up being straight across. Okay, so we still have the velocity of the water with respect to the ground is still going to be in this direction. So let me just draw that. Let's label this one now. This is going to be the velocity of the swimmer with respect to the water. And then her net is going to be straight across, right? The velocity of the swimmer with respect to the ground is simply going straight up. So if we're trying to find how much time it takes to get across, well, again, I would simply write an equation like this, right? The distance to get across is still d, the width of the river. And now look at the y component. The y component we're looking for is the only thing with a vertical component right here is going to be this velocity of the swimmer with respect to the ground. So if I can find this value right here, I'd be able to solve for the time. Okay, because I could just rearrange this equation. D is velocity of the swimmer with respect to the ground. All right, so how do I find this magnitude here of this velocity? Well, now you can use Pythagorean theorem, right? Because we still know that this here is still 6 meters per second. I also know that the river is still flowing here at my, what did we find before? 4 meters per second. Okay, so we have to find the magnitude of, or the speed of the swimmer with respect to the ground. Now you could either find the angle and then use some trigonometry, or from Pythagorean theorem, I should be able to write right away that this will be velocity of the swimmer with respect to the water squared minus the velocity of the water with respect to the ground squared. Now we substitute our values here, and this is what I get. So here I get 6 squared minus 4 squared. So that gives me a value of 36 minus 16. That gives me root 20 as my speed. So now we go back at the top equation right here. My distance is still 90. And then I divide by a root of 20. And at the end of the day, I get something like 20.1 seconds. Okay, 20.1 seconds. B is the closest choice to that, solution. All right, great problem. Let's go to the next one now. All right, problem 2, we have 3 airplanes of identical technical specifications and air speeds of 260 kilometers per hour depart from an airport on a day when the wind is blowing from west to east at speed of 45 kilometers per hour. Plane A sets a heading of 17 degrees west of north. Plane B orients itself due north. Plane C orients itself 17 degrees east of north. All right, our first question says, after 15 minutes of flight, which plane has gone the furthest north? Well, let's have a look at these different scenarios. So this here is plane A. It is going at a velocity here. This is of the plane, again, relative to the air, okay? These are all the different cases. So this is plane A. Plane B is going straight up like this. And then plane C is going like this. Okay. Now the key to all of these things is that the plane relative to the air, those vectors are the same for all of the 3 planes. Those are in kilometers per hour. So which one's going to go the furthest north? Well, let's think about it. The one that's going to go the furthest north is the one that has the biggest component of the velocity that is pointing north. Okay. Clearly point A and point C, again, if all of these 3 vectors have the same magnitude, if you break the vector A, for example, into components, it has a component here that is along the north direction, but it also has a component here that is going to be along the west direction. And this component here along the north direction for A and for C is going to be smaller than that of plane B, because plane B has its 260 kilometers per hour that is directly pointing north. Therefore, that is the one that is going to end up going the furthest, because imagine we're going to write my y displacement as being, what is that vertical velocity, let's call it Vy, multiplied by how much time we're flying. Each plane flies for the same, right? Same 15 minutes. So it's whichever one has the largest Vy is going to go the furthest. So that has to be plane B. All right, what do we have next? The next problem says, after 30 minutes, which plane has deviated the least from a line on the ground that runs straight north? All right, so again, what we end up thinking about now is, what does everything look like? So what we really got to think about is, what is the velocity of the plane relative to the ground for each one of those cases? Okay, well, plane B is going to fly straight up, but the wind, we can't forget about this wind here. The wind will make it shift this way, right? Because the total plane relative to the ground expression should look like this. It's the velocity of the plane relative to the wind plus the velocity of the wind relative to the ground. Okay, this is how you write this vector sum. Okay, so the one that is going to have, for example, the smallest east-west component is the one here that can cancel a little bit of this component. So it's clearly going to have to be plane A, right? Because plane A has some component that is along the west direction, and that there could cancel a little bit of what's going on here with the wind, which is pointing east, all right, or has a velocity in the east direction. So for this one right away, I think I would simply conclude that plane A here has to be the one that is going to go the furthest straight across. All right, the next problem says, after 1 hour of flight, how far is plane C from the airport? Okay, so we're really looking at this plane over here. All right, so what we have to do now is figure out this expression over here for plane C. Okay. If we want to know how far it is, you want to know the distance, we simply need to know the speed of the plane relative to the ground multiplied by our time, which is going to be 1 hour. So as long as we can figure out what is the speed of the plane relative to the ground, we're going to be in good shape. Let's first find the vector of the plane relative to the ground and then find the magnitude of that vector. All right, let me give myself a bit more space and let's substitute what we know for this case. So what is the plane relative to the air or relative to the wind? Plane C is orienting itself 17 degrees east of north. So the way that I would write the plane relative to the wind, I would write it like this. The magnitude is 260. However, it does have a vertical component and it does have a horizontal component. So let's write down that horizontal component here. So that would be, and this angle here is 17 degrees, just call it theta. So this here would be sine of 17 degrees, okay? And what else? Its vertical component here would be 260 cosine of 17 degrees. All right, that is our first vector, the plane relative to the air or relative to the wind. Now here we also add the wind relative to the ground. So the wind relative to the ground is what is going on right here, and it's only blowing east, so it only has this x component. So the x component here would be 45 and comma 0. It has no vertical component, no north-south component. All right, so now we simply have to find what are these two components. So this is the plane relative to the ground. You put those numbers in your calculator. I think I got something like 121 for here and 249 approximately for here. What I'm really interested now is the speed, so I want to find the magnitude of this vector right here. So what is the magnitude of this guy? Now you simply use Pythagorean. So I do 121 squared plus 249 squared. Take the square root of that. I get approximately 277 kilometers per hour when I do that. All right, and now you're simply multiplying this by 1 hour. So if I multiply that by 1 hour, I'm going to get 277 kilometers per hour multiplied by 1 hour gives me a total distance of approximately 277 kilometers. Okay, so that is kind of the best solution, and that corresponds over there to choice A. All right, kind of a good problem. Let's go to the next one. Problem 3 looks like this. Two houses are located on opposite sides of a river as shown over here in the diagram. The width of the river is 247 meters and the river flows in the positive y direction with a speed of 1.3 meters per second relative to the houses. A boat sets off from the left house moving with velocity VBR relative to the river. The y component of VBR is 2.1 and the y component is 3.1. I'm sorry, the x component is 2.1. All All right, first question says, what is the speed of the boat as measured in the reference frame of the house? All right, what I would suggest here is let's write down an expression for the velocity, and then you can find the magnitude at the end of the day. So what we're looking for is the boat relative to the house. What we're given in the problem is information regarding the boat relative to the river, right? So we're going to insert the river over here. So I write this as a vector sum. This is the boat relative to the river plus the velocity of the river here with respect to the ground or with respect to the houses. Now each one of these vectors you should be able to write down. So how would I do the boat relative to the river? Okay, so that is the information given in the problem. So we have an x component which is 2.1 and we have a y component which is 3.1. So this is what this vector looks like. This is 2.1 comma 3.1 as my vector. Plus, we have the velocity of the river relative to the house. That is our 1.3, and it's only flowing, if you look, it's only flowing in this y direction. So it has no x component, and it's flowing at 1.3 meters per second. So you go ahead and you calculate that vector, you should get 2.1 for the net x component, and here we're going to get 4.4 for the net y component. At the end, if you're looking now for the speed, okay, what we're looking for is what is the magnitude of that vector. Okay, now we can again just simply use Pythagorean. You could square both of those components, 2.1 squared plus 4.4 squared. At the end of the day, we get the solution, which is 4.88 meters per second. All right, so the best choice for this question is choice A right here, 4.88. All right, next problem says, when the boat reaches the other side of the river, how far is it from the nearest house? All right, let's draw these vectors and see what this looks like. So we've got the boat relative to the river, which is flowing, which is in this direction. That is the boat relative to the river. We have its components. And then what else? To that, we're going to add our second vector. This is going to be the river here with respect to the house. So I should sneak in a velocity here. Let me just clean that up. So this guy here is the velocity of the river with respect to the houses. So this is really what the boat is doing if someone's standing on the shore relative to the houses. This is the velocity of the boat relative to the house. Okay, so what do we want? This whole vector here can be written down into two components, which we have here. Now, it's going to be closest to the house here on the right-hand side because it's clearly going to be on the other side of the river. Okay, so how could we figure out how far away it is from that house, which is kind of located down here? Okay, that's the house. So you need to look at the total y component of my velocity of the boat relative to the house because we're looking for that displacement, right? So for that, we need to know the speed, but only the y component of that velocity. So let me write boat relative to the house, but we're really only looking for the y component, and we need to figure out how much time does it take to cross that river. Once you know this, then you can calculate how far away you are. So for the time, guess what? We're going to use the information in the x direction because you know the width of the river is 247. So right here, we know that this here is going to be the width. And what is the x component of my velocity? It's 2.1 in this case, right? It's the speed of the boat relative to the house, but only the x component. So this is how you can get the time from this expression right here. It's simply going to be the width divided by this x component of that vector. All right, so you could substitute this in right away, but I'm just going to instead just substitute this whole expression up above and then punch in the numbers. So we're going to substitute time right here to get my y displacement. All right, so my y displacement at the end of the day is going to be my y component, VBHY, and multiplied by the time. The time here is going to be the width divided by VBH, the x component. So now you substitute in all the values. So our y component was 4.4. Our x component was 2.1. And the width of the river was 247. All right, we put all of those numbers in the calculator, and you should get something that is close to 517.5 meters. All right, so the best choice here for this question here is choice A. Our next question says the time it takes for the boat to get to the other side in the above scenario is t naught. Now suppose the driver of the boat steers in such a way that the boat moves along the x-axis directly from the house on the left to the house on the right. If the speed of the boat relative to the water is the same as in the original problem, compare the time it takes to get across the river in the new case, t new versus t naught. All right, I'm going to give myself a little bit more space to work on here, so let me just kind of erase some of the previous stuff. All right, so this is what we had in the first case, right? And in this case here, we're going to call this time here is going to be t naught. Okay. Now, t naught is determined by what? Well, t naught is really determined by how much time does it take to cross this direction here, the width. So what would be kind of an expression for t naught? Well, we know we want to cross the width, and what we're looking for is only this x component of VBR in the x component multiplied by time. Okay? So the time in both cases will be the width divided by what is the boat relative to the river in the x direction only. If we can make changes to this, that is going to affect the time because we're not changing the width of the river. Okay? So for case number one, what we have is VBR in the x direction is simply equal to 2.1. So what we have to do now is you have to look at what happens in this second case. So let's go see what the diagram looks like, at least the vector diagram for t new. So t new in this case, again, I'm going to have to direct my boat so that it's going downstream. Okay? And the vector, this total magnitude, is going to be the same. Okay, so I could really figure out how long this vector is, but it has to be oriented downstream because the river hasn't changed also. The river is still going upstream. So this is the river relative to the house. And what I want is I want the vertical component of boat relative to the river, that vertical component, to exactly cancel this out. Okay, so what does that mean? That's going to mean that my net of the boat relative to the houses, right, my velocity of the boat relative to the house is simply going to be in the horizontal direction. Right, so we have to really compare what is this x component of this vector right here. It's only going to be whatever the x component of this guy is. Okay? Now what you're going to see here is that the y component simply here has to be minus 1.3 meters per second. Okay? In the first case, the y component was 3.1. Okay? And since we're not changing the length of the vector, we know right away that the x component here of VBRx is going to have to be a bigger number because in both cases the magnitude is the same. So I only have to direct a little bit of an angle in order to cancel out the river with respect to the houses. So at the end, really what I'm going to get is my t new is going to be the width. And now my velocity of the boat relative to the river, at least the speed of the boat relative to the river, that x component of it, this guy here is going to be a bigger value. Okay? If that's a bigger value, it means that the new time here is going to be a lot smaller than the previous time. All right, so this is choice A. Really, without doing any numerical calculation, we should be able to make this deduction. All right, here's problem 4. It says the houses A, B, and C are located on the river as shown. House B is on the same side of the river as house A and is a distance of 600 meters away. House C is directly across the river from house A and is also 600 meters away. The river flows in the y direction with a speed of 1.1 meters per second relative to the houses. Your boat can move with a maximum velocity of VBR 3.3 relative to the water in the river. All right, the first question says, what is delta TAB, the shortest time in which you can drive your boat from house A to house B? All right, well, if I want to start over here at house A and end up over here at house B, the best way I should do is just to aim my boat directly in the y direction, right? In that case, I'd be adding my speed of the boat relative to the water plus the river relative to the house, right? Really what you're doing here is you're saying that the boat relative to the house is equal to the boat relative to the river plus the velocity of the river relative to the house. Okay? What you want to do in the first problem here is you only want to aim it exactly in the y direction. So you get 3.3 for that one. And the river relative to the house is also only in the y direction, and this is 1.1. So this here gives me a velocity of 4.4 meters in the vertical direction. Okay, that is the fastest you can go in any direction, actually. All right, so I'm looking for the time. Well, I know that my y displacement is going to be whatever the speed was multiplied by the time it takes me to get there. So the time is going to be that distance in that vertical direction divided by that velocity in that vertical direction, or by the speed rather. So my distance here is 600 meters. The maximum speed I could get is 4.4. I put those numbers in the calculator and I should get something that looks like 136.4 seconds. All right, for the time. So that there corresponds to choice B as being the best answer. All right, next problem says, what is delta TBA, the shortest time in which you can drive your boat from house B to house A? So now you're going in this opposite direction. Well, again, it's going to look similar to the above expression, except now the boat relative to the house, well, let's think about it. If I want to go back down in the negative y direction, I want to move my boat like this. So my vector here for boat relative to the river should look like this, minus 3.3. Now the river hasn't changed. This is still 1.1 in the y direction. So at the end, my speed ends up being, well, has a magnitude of 2.2 meters per second going down. That's the fastest you can actually move. The distance hasn't changed, so my time is still going to be my y displacement divided by the speed, which is just the magnitude of that vector. So this we're going to get 600. And here we're going to get 2.2 as the magnitude. So that there corresponds to a time of 272.7 seconds. All right, so for this one, A is the best choice. All right, next problem says, what is delta TBA, the shortest time in which you can drive your boat from house B to house A? So now you're going in this opposite direction. Well, again, it's going to look similar to the above expression, except now the boat relative to the house, well, let's think about it. If I want to go back down in the negative y direction, I want to move my boat like this. So my vector here for boat relative to the river should look like this, minus 3.3. Now the river hasn't changed. This is still 1.1 in the y direction. So at the end, my speed ends up being, well, has a magnitude of 2.2 meters per second going down. That's the fastest you can actually move. The distance hasn't changed, so my time is still going to be my y displacement divided by the speed, which is just the magnitude of that vector. So this we're going to get 600, and here we're going to get 2.2 as the magnitude. So that there corresponds to a time of 272.7 seconds. All right, so for this one, A is the best choice. All right, the next one says, what is delta TAC, the shortest time in which you can drive your boat from house A to house C? Well, let's have a look at this one. So really what you want to do now is if I'm at A and I want to end up straight across and the river is flowing downstream, what you have to do here is you have to orient your boat at some angle over here. So this here is really the velocity of the boat relative to the river. Okay, because what are we going to be doing now? Well, the river is still going to be pushing the boat like this. This is the velocity of the river with respect to the houses. What you want at the end is this net velocity here to go from house A to house C. So you're going to go directly across. So this is what you call the velocity of the boat relative to the houses. All right, so it's really this first equation that we had here, but now we have to include these components of the vectors. Okay, what we're going to know now is that the magnitude of this guy is still my 3.3, but it's at an angle. And what else? The river relative to the houses, that one hasn't changed. The magnitude of it is still 1.1 meters per second. So let's set up, see if we can find what this angle is, number one. And then once you know the angle, you can probably find what this velocity is, boat relative to the house. Then you have to calculate the speed in order to get the time. Okay, so let's set up that equation. So first we're really looking for that x displacement, which we know is still d. That's 600 meters to get across. So to get across, I need to know what is going to be the speed of the boat relative to the houses, and that it'll be multiplied by how much time it takes. So you can see from our expression here that the time is this 600 meters divided by the speed of the boat relative to the house. Okay, so this is the end goal, and the only unknown in this equation is the speed of the boat relative to the house. So in order to find that, we go to our top equation. Let's also find what the angle is, right? The angle, you should be able to find it using trigonometry at this point. For example, if you use sine of theta will be 1.1, the opposite over the hypotenuse, which is 3.3. Now, if you put that in your calculator, you should get an angle theta that's approximately like 19, say 0.47 degrees. All right, now what we're going to do is find the velocity of the boat relative to the houses. Okay, so if you look at this black vector over here, it only has an x component. Okay, so what I would do is I would simply write that as velocity of the boat relative to the house. It has no vertical component because I just want to end up going straight across in this direction. That there is the sum of two terms over here, right? We have the boat relative to the river, and what I want to do is write that in terms of an x and y component. So the x component of this guy should be 3.3 multiplied by cosine of the angle theta. Okay, that 19.47 degrees that I just solved for. The y component is minus 3.3 sine of that same angle theta. To that, I want to add now what is this vertical component of the river. I can write that in terms of an x and a y component, and it looks something like this. All right, so you can see right away the only thing we're really interested in here is this guy, and it's only this x component of the boat relative to the river. All right, so this guy you could solve for. If you put those numbers in the calculator, you should get something like 3.11 meters per second. Now you can go back in my top equation over here and write that the time is going to be my 600 meters divided by that 3.11 meters per second. All right, it gives us a time of approximately 192.8 seconds. All right, 192.8 seconds corresponds to choice E as being the best choice for this problem. All right, let's go to the last problem. All right, in a triathlon, a contestant swims in a straight line from start to finish in a time t. In order to do so, the contestant has to swim against the flow of the river, which has a constant speed v relative to the ground. They're asking you, what is the x component of the swimmer's velocity with respect to the water? Note the variables used in this equation are all positive. Okay, and we have 5 choices right here. I think the first thing I would do is I would set up an expression for the swimmer here relative to the ground and write its velocity. First, if he's swimming along this path, it means that this vector here must be in this direction here. This is really the swimmer relative to the ground. How would you write this as the sum of 2 vectors? I would write it as the swimmer relative to the water. We are looking for the x component of this vector plus the velocity here of the water relative to the ground. What I've done here is I've inserted water here in between both of those letters using my standard approach. All right, now if you think about the left-hand side, we know everything about this because we know that it takes a time t in order to swim across. And if you're drifting downstream a distance d, guess what? It means that the x component of that vector here must be d divided by t. The vertical component here has to be, well, it has to be related to that width. The vertical component is going to be the width divided by t right here. Okay, so we know the swimmer relative to the ground in terms of all those variables. What we're looking for here is the x component of the next vector. So I can simply write it as an x component here and a y component, but we only really want to solve for this guy. All right, what's the next thing I know? Well, can I write the velocity of the water relative to the ground? The water relative to the ground is shown right here in the figure. It is flowing to the left. So the way that you should write this vector, again, look at our coordinate system that we have set up right here. We have positive x going to the right. Therefore, this guy here should be minus v term because v is a positive number. All right, and that there is 0. So at the end, the only thing you have to do is rearrange this equation for Vx. Solving for Vx, what do you get? D over T, and then plus V would be kind of the best approach. I'm just bringing the minus V on the other side. All right, and that there corresponds to choice A. And this one here physically makes sense, right? Because we'd expect Vx to be bigger than V, okay? It can't be kind of these guys. It can't be this one. It also can't be this one. It has to be bigger than V. Only A and B are actually bigger than V, because if you think about how do you end up right here at the finish line, the vector diagram, the way it looks like is it should look something like this. You actually have to swim like this. This is the swimmer relative to the water, because in this case, what do we have? We've got the river that is pushing you like this. This is the velocity of the water relative to the ground. At the end, you're going to be left with this net vector here, which is the velocity of the swimmer relative to the ground, right? And that's where the finish line is, right at this point, right? So we expect that the x component of the black vector here, the swimmer relative to the water, this is the x component, right, has to be bigger than the x component of the water relative to the ground. Okay. All right, that is a great problem, and thanks for watching this problem set. Hopefully you enjoyed it. We'll see you next time.